All right. Hello, everyone. Welcome back to Advanced Plus Plus. Today we're going to be going over autoencoders. So, yeah, this kind of machine learning architecture is pretty different from a lot of the other things we've looked at in the past. You'll notice a lot of stuff from the Transformer workshop might ring a bell here when we talk about autoencoders. So, yeah, let's just hop into it. So, this is our schedule. So, yeah, it's week 8. And we're doing autoencoders, and this is actually going to be the last workshop. We originally had one more, but we had to move that to next quarter just because of logistical reasons. So yeah, this is actually our last Advanced Plus Plus workshop, and hopefully it'll be a pretty fun one. I think we can get through most of the content pretty quick, and this is a model and a kind of idea that's used very, very commonly in most machine learning applications. So you'll see it almost everywhere. So here's the resources. So as usual, the link to the slides, the feedback form, and the collab. We're going to do a little demo of the collab for you guys this time around. And the membership portal code is TULIP for anyone who's here live. So yeah. And then Justin, do you want to talk about this?
Sure. So, as part of a wider ACM AI initiative held by our outreach and events team, we are trying to promote our You Belong in AI podcast. So, it's a podcast in which we interview different individuals within the AI community about their background, how they got to where they are, and the work that they do. Um, Specifically highlighting the importance of representation and inclusion within AI. So they just released their most recent episode where their guest is Cornell PhD student Chinasa Okolo. So be sure to check that out. There are also other guests that we've had previously that you can find on the same page. So just follow that link and you should be able to see it.
Yeah, this is a link. It's not for Or wait, I was muted. Okay. Yeah, I was saying this is actually a link right here. It looks like the title, but it's you can actually click on this. Yeah. Okay. So yeah, let's dive into it. So we're just gonna give an um, overview of autoencoders and a variation on autoencoders called Variational Autoencoders. And then we're gonna do a little coding demo, and hopefully it should uh, be pretty quick and fun. So yeah, let's get into the content. So yeah, what is an autoencoder? So the goal of an autoencoder might initially seem like kind of like trivial and useless. And if yeah, it sort of is on the surface, but we can actually do some pretty useful stuff with it. So the big idea of autoencoders is we want to take some input and then we want to, as precisely as possible, copy it to an output. So if we pass it like an image of a cat, we want the output to be like also like an image of a cat that looks like exactly like the image that we gave it. Um, Now, yeah, this might raise some initial questions that are like, okay, well, this seems like not very useful. Like, what's the point of this? Like, how is the network learning anything? These are all questions that will be answered very soon. So, yes. Um, so, yeah, I guess on the slide, it kind of gives a hint towards this. So, we're actually trying to learn the representation for a particular set of data. So, what that means is the whole point of the autoencoder, what we care about is not the actual output. Um, the output's sort of like a byproduct of what we actually care about. What we actually care about is the weights that are learned um, towards what we call a latent space in the kind of hidden layers of our neural network, which is the autoencoder. And what we want it to represent is higher level features of the of whatever data set that we're looking at. So if we're looking at like images of animals, for example, we want to basically extract a bunch of higher level information about um, the animals, right? And in most neural network architectures that we've looked at, we're actually doing something very similar to this. If you guys remember, like kind of the idea behind a standard neural network is we basically want to dissect like some low level information. So for example, like an image of an animal, we want to dissect that low level information through multiple hidden layers into something that's hopefully um, linearly separable. So that would mean that would have to be extracting higher level information. And then based on that linearly separable data, then we're able to kind of classify the output as a cat, dog, or whatever animals that we may be looking at. One caveat to that, you could be like, okay, why do we need autoencoders? Like, great, we can do this. Like, we can kind of learn features like over multiple layers, extract higher level features through multiple layers in a normal neural network. Well, in normal neural networks, we have labels for our images, right? Or if we're looking at images, basically we have labels for our training examples. So we're doing supervised learning. Now, what's different about autoencoders is that we don't actually have the labels for our images. So we don't have a labels for each image saying, oh, okay, we pass the network an image of a cat, and we also have the label saying this is an image of a cat. We don't have the label. We only have the image. But we still have to somehow be able to learn some some like higher level information about the image despite not having any labels to go off of. So this is going to have to slightly change kind of the structure of a traditional neural network that we've had in order to meet this kind of new situation in which we don't have labels. And this is where we get the structure of the autoencoder. So yeah, this is kind of what an autoencoder looks like. So the first thing we do, or yeah, I guess there's two kind of pieces to the autoencoder. So the first piece is sort of the encoder step here. And then we also have this kind of middle area called the latent space representation. And then the other part of it is called the decoder. So the job of the encoder is to do what I've been kind of saying for the past few minutes. It's to be able to extract high level kind of information from some sort of data. And then we want to encode that in some sort of latent space. Okay. But in order to actually make this happen, in order to train this in a way that's possible, we need something called a decoder. And the point of the decoder is to kind of take some piece of high level information that our encoder has taken from the image, and it wants to be able to reconstruct that image from only that limited high level information. So for example, if we pass like an image of a cat, this is just a bunch of RGB values, right? We want to be able to encode this to some high level information, maybe like some value that just automatically represents like, okay, if this is lit up, then like construct like an image, this image of a cat, right? And then what will happen is that this decoder will take that point from that's in this latent space, and then it will reconstruct it. And then it should be able to identify and learn, okay, if I sample this point from my latent space, I should be able to reconstruct this image of a cat, hopefully as perfectly as possible. Okay. So this is just another like way that we can look at this. That's maybe I guess more 2D. Yeah. So we have like some original input, right? So maybe this will help make more sense. So you have some original input. So in this case, it's a handwritten digit, right? So we pass it through the encoder, and then it's sort of, yeah, because we're extracting higher level features from the data, you can think of it as basically we're just compressing the data. Okay. So you can think of like the whole autoencoder as first compressing data to some lower level space, and then then the decoder will decompress it to get the original input. And hopefully we've seen in compression and decompression schemes that if we're doing a good job, hopefully this reconstructed input that we get after we decompress is as similar as possible to the original image, right? Because if we have a perfect scheme, then hopefully we'll get the same thing as our output. Now, this sounds nice. Um, like cool, like we can just do this and then we can reconstruct the output, right? But what happens is we need to impose a lot of regularization on this model for a couple of reasons. And the main reason is that if we just leave this model unconstrained, we just have some encoder. So this encoder can just be like anything that we've like seen in the past. It can be like a convolutional neural net, something that has like convolutional layers. It can be like a fully connected network, right? It can be anything, things that we've seen before. This isn't some foreign concept. We're just like labeling it as an encoder in the context of this autoencoder structure. Okay, so yeah, this is great. Like we can just like have some encoder, compress our information, and then decompress it, and then we could just say, okay, if we're doing this perfectly, then like cool, our job is done. But the problem is our initial job. If we remember what the initial job was, the initial job isn't just to reconstruct the input. The initial job is that we want this latent space, this thing in the middle, to actually be representing higher level features. So what happens is if we don't impose any sort of regularization, if we just leave this to be basic and exactly what we're looking at, no constraints imposed, what happens is that we won't usually actually learn higher level information here. we're just gonna like maybe learn some like I don't know, some like rote algorithm that will just like say, okay, if this point lights up, then it's this image. So just reconstruct this exact image for me. If it's this other point, if this other point is lit up in our latent space, then construct this other image. So this can be thought as memorizing the data set, right? This is a form of overfitting. Just how we've seen in normal neural networks, if we are overfitting to our training set, what will happen is instead of the network learning higher level features of the data and using that to make a prediction, it'll instead just memorize all of the images that it's been fed, and then this is why it will do things like not perform well on the test set, and actually it won't actually perform well on deployment, right? So it's a similar concept here. If we don't perform any sort of regularization, it'll just learn an encoding such that it can only like make good reconstructions based on like images that it's seen before. And as a result of that, instead of actually learning higher level features, it's kind of just memorizing the data that we've been feeding it. And this is literally useless, right? Because at this point, all we have is a copy network, right? We just feed in the image and then it throws us out the output, which on its own isn't useful. What makes this useful is this latent space representation. And we're going to talk about what's so useful about being able to generate higher level features in a couple of slides. Um, but like there's many applications in machine learning in which it's very useful to basically construct some sort of compressed representation of our original input that is kind of like um, smaller or higher level, right? Like the most obvious example of this, I guess, which isn't usually why we do this in machine learning, but one obvious example is, oh, if we can compress the representation and then we use this representation to like train normal neural networks instead of the original image, well, this takes up less space usually, right? Because it's like a compressed representation. So that's one very trivial reason why this might be useful. But there's many other reasons why this is extremely useful in machine learning. So yeah, let's move on. So yeah, so like let's just like walk through an example of what happens like kind of with this handwritten digit of this 2 for example. So yeah, this image comes from the MNIST data set, which we've talked about back in advanced track and in other workshops, right? So we have like monochrome 28 by 28 images. So 28 by 28 times 28 is 784. So then yeah, we would just represent this as our input as like just 784 neurons, just like back in advanced track when we were first learning about basic feed forward fully connected neural networks, how we would unwrap this image into 784 pixels and then we would just pass it through the network, right? So first we're just going to do that. And then the second thing we're going to do, so this is our kind of full autoencoder structure here. The second thing we're going to do is we're going to kind of, in this case, I think, yeah, we have, it's just a fully connected layer, right? So in our case here, our encoder is represented by this kind of set of weights here, all these connections, and it's just representing a fully connected layer, or yeah, one fully connected layer, just like we would have in a normal neural network. And then what we have here is just like another set of hidden layers, hidden units, right? And this hidden unit or these set of hidden units is what our latent space is going to be encoded into. And then our decoder is just going to be represented by another set of fully connected weights that go from this latent space to our output space. So if we imagine what happens here, so we unwrap this 28 by 28 image into 784 pixels. And then, yeah, so our encoder is just going to hopefully what the job of the encoder does is like in this example, we have 784 input images or input pixels, but then our latent space here is only 5 neurons, right? So we can see how we're encoding this into a much lower dimensional space, right? And that's what the job of this encoder here is, this set of weights is to somehow make this projection from these 784 inputs into these 5 inputs without losing much information, while preserving as much information as possible. And then if we preserve as much information as possible here, we can also imagine that would make the life of the decoder easier, right? So now we take this kind of compressed image, and then hopefully our decoder, if it's learned correctly, is going to be able to reconstruct 784 values that hopefully are as close as possible to this original input. Okay. Um, so yeah, you might be wondering, how is this trained, right? Because in all of the previous workshops that we've talked about, we've said, okay, like we're doing supervised machine learning. So we have labels on our input, right? So when we pass our input, we have some loss here at the end when we compute our scores, and then we compute the difference between the scores and the scores that our network provided and what the actual label is, right? And as we know, like if our output prediction of our neural network is very good, so if it correctly identifies it, then our loss is going to be very small, because when we compute the difference between the actual value and the value that our network predicted, they're going to be very close to each other, right? But here we don't have any label to compare to. So what we do instead is we simply compare the output that we get, the difference between the output that we get and the input, right? Because we've been discussing the whole time, right, that the criterion for this network is we want the output to be as similar as possible. So let's test for that, right? So instead of using a label, let's just pretend our input is the label, right? Because if the whole point is to reconstruct this, then the farther off our output is from the input, the more loss we have, right? So what we'll do is, instead of using a label, we'll just use the input that we passed into the network. And we can imagine, right, that if we're doing a very good job of reconstructing the input, then the difference between the input and the output is going to be very small, and then we'll have a loss close to zero, which is like always what we want, right? We want to minimize the loss. So that's that's sort of how we get around not having labels. And that's what's so beautiful about the autoencoder structure, is that we don't actually need labels to do this, right? Okay, so I've mentioned in the past couple of minutes how let's not lose track of what the actual goal of the autoencoder is, right? So we're saying the criterion we're using to train the autoencoder is that we want the inputs and the outputs to be as similar to each other as possible. However, we said, like we said, this is meaningless unless our latent representation is actually learning higher level features of the input space, because that's actually what we care about. And we were saying that if we don't do any regularization and we don't enforce and kind of put any restraints on the network to make it kind of prevent it from just memorizing the data that we give it, instead of actually learning higher level features, it's just, like I said, it's just going to memorize the data. So then that's going to yeah, that's going to result in, like I said, overfitting, and we're not actually learning what we want to learn. We're just learning a copy network. Okay. Um, so what do we do to combat this? Just like how we combated overfitting in our kind of traditional neural network architectures, our convolutional neural networks, our recurrent neural networks, are fully connected networks. Just like we imposed regularization and different methods of trying to prevent overfitting, we're going to do a similar thing with our autoencoders. And what this is going to do is it's going to allow us to actually learn higher level features. Now you can imagine, right, that if we're imposing additional constraints on the network, you'd imagine that this output reconstruction might not be as good, right? Because we're kind of giving it less tools to work with. But this has always been the point of regularization, right? We're restraining the network in some way, but we still want it to be able to do the task that it's been asked to do as well as possible, right? So this is one way that was enough overview. This is what we actually do. So what we can do is, theoretically, instead of only having like 5 hidden units here, we can actually have a lot. Let's say even like 200, right? We can have like 200 hidden units here, right? Now, like we've seen with normal neural networks, if we give it too many units, right, it's gonna make the network more prone to overfitting and actually memorizing the data instead of doing what we actually want it to do. So despite having a large number of hidden units, we can do a lot of things that regularize the model. Okay. So what we can do is introduce this idea of sparseness, which we've indirectly looked at actually exactly this same thing in our optimization and regularization workshop a few weeks ago. So what we discussed a few weeks ago in the optimization and regularization workshop is that L1 regularization. So what we discussed L1 regularization is when we just append kind of the magnitudes of the weights to our loss, right? And then that kind of forces our weights to stay down, right? So we said what happens when we introduce a scheme like L1 regularization is that it's going to drive a lot of our weights down to zero. And we had a nice discussion of why that drives a lot of the weights down to 0 in the optimization and regularization workshop. So I'm not going to go over that again, but we should remember that this is a property that L1 regularization has. So basically, it'll cause some of the weights to converge straight down to 0. And we can observe the effect that that has, right? Especially in this context of our autoencoder, is that if we push some of the weights down to 0, that's kind of turning off some of the hidden units, right? Because now this connection is disconnected. Maybe this connection's also has this weight also has a value set to 0. So it's kind of introducing sparseness in that we're kind of deactivating some of these um, we're kind of deactivating some of these neurons in our latent space. Okay, so this acts as a regularizer for the exact same reason that we discussed. It acts as a regularizer in our optimization and regularization workshop, right? When we force some of the weights to be close to 0, we discussed many reasons why this is good for regularization, right? It makes for example, it forces perturbations in the input to not have as drastic of effect on the loss. It also kind of acts as an ensembling, or not an ensembling method, but it's sort of similar to dropout, right? Because if we turn off some of the neurons, this is sort of in a sense what we did with dropout, how we were randomly turning off some of the neurons every single time we fed forward through our network. So it's very, very similar to what we've discussed in the past. It's precisely exactly the same thing. We just use different terminology to describe it here in the context of autoencoders, because we're dealing with autoencoders and not with traditional just feed forward neural network classification tasks. So I'm going to stop a second for questions, because I haven't stopped in a long time for questions. Okay, cool. As always. Oh yeah, go ahead.
I'm not really sure what's the purpose of autoencoders, like why we wanna reconstruct the picture.
Yeah. So we have a slide. Yeah. So yeah, maybe we should have put this slide towards the beginning of the workshop, but we have a slide that kind of describes why this is useful. So like I said, the criterion that we use to train, so like the condition that we use to actually train the network, is that we want this output to be as close as possible to the input, right? But we said we don't actually care about the output, right? Because like you're completely correct in saying like, why is this useful, right? If all we're doing is reconstructing the input, why is this useful? And the reason it's useful is because of these hidden units. Okay, now this is why this might be a bit confusing, because this is kind of different from what we cared about in our traditional neural networks, right? In traditional neural networks, we cared about the output. We cared about getting the correct output. We didn't actually care too much about the hidden units. We were like, okay, the hidden units can be whatever, they can do whatever they want. That's not of concern to us. All we care about is if I give it an image of a cat, if we're doing a classification task for animals or something, if I give it an image of a cat, its output should tell me this is an image of a cat. That's what we cared about, and we didn't care about what it did in between to get there. What's different about autoencoders is that we're now concerned about this in between part. We're not as concerned about the output. We're concerned about what it's doing to get to that output. Okay. And we're just, so what I've been discussing is that the point of the autoencoder is we want this hidden area, the job of it optimally to extract higher level features from the input. So basically you can imagine, right, like any compression scheme, right? Like when we zip like a file in a computer, right? Like let's say a file's 10 kilobytes, right? And then we zip the file and we want it to preserve somehow. We want it to only be like 5 kilobytes now instead of 10 kilobytes now. But then we want it so that when we unzip it, it still gives us like the same exact thing, right? Like, or at least very close to the same exact thing, right? So this is what we're doing with autoencoders. We're kind of developing a way to compress this input. That's what we care about. So we want it so that at this intermediary step with these hidden neurons, um, we want this activation, the values of these activations in this hidden layer, we want them to be a compressed version of the input. So that's what we care about. We want to compress the input.
And so we want, is it because we want to store the data in more like smaller capacity?
Yeah, so there's many reasons why this is useful. So that is one like reason that I brought up earlier why it's useful. Yeah. So theoretically, you could just use this, like you said, as a compression scheme where, okay, I have a bunch of like, I have 784 like pixel values. I This takes up a lot of space. I can make them, maybe I can use an autoencoder to like, so it takes up less space. You could do that, right? But this isn't super good because if you really just cared about that, you could just use a compression scheme, right? You could use like something like Huffman encoding or whatever genius compression schemes like developers have come up with, right? So there's that is correct. You're correct in saying it does accomplish that. It also accomplishes many other things because it can extract higher level details from the data. I'm actually sorry, Justin. I know we wanted to keep this towards the end, but I think it would be helpful to talk about this now. So yeah, we actually have a slide about this, why we use it. So yeah, it's useful not only because it takes up less space, but that the space that it's like the thing that's being stored is kind of very rich information about the data. Um, Now this is useful for a bunch of reasons, right? So this can do something called dimensionality reduction, which intuitively this makes sense, right? Because if we have 784 neurons and then we put it into a space that's like only 5 neurons, like we're reducing the dimensionality. This also does something called data denoising, right? So this is one like kind of example of where this is very useful. So imagine that you have a bunch of like pictures of cats, dogs, etc., right? But they're not very like clean images. So there's a lot of noise. So that could mean the images are very blurry. That could mean like there's a lot of like um just like it's not a very precise image, right? So I guess the easiest way to think about it, like imagine like the image is very blurry, right? So that means it's like a very noisy image. So the good thing about autoencoders is like optimally speaking, if I have a pretty noisy image of a dog, so let's say I have a pretty low resolution image of a dog, and then I have a pretty high resolution image of a dog, what will happen optimally is that in a perfect world, you would pass both of those images through your autoencoder, and then in the hidden layer, in that middle layer, when we get the compressed version of it, those two compressed versions should be very similar to each other. So it should be less susceptible to noise in the data. So despite the data being very low resolution, we were still able to get kind of a high level extraction of the information that contains all of the same information that the actual image of the dog had. So hopefully you can imagine why this is useful, right? Like in many real world scenarios, we're going to be confronted with very noisy data. So let's say like we do want to do a task where like we just want to identify, oh, is this a picture of a dog or is this a picture of a cat, right? But all of our data is very noisy, right? So what we could do is first we could train an autoencoder, and then yeah, so first we can train an autoencoder in the ways that we've described throughout this workshop. And then once you've trained the autoencoder, pass the images through the autoencoder, and then instead of using the original image as your input to some classifier, you could use the compressed image. You could use that compressed, you could use that kind of the activations in that hidden layer in that latent space, and then you could use that as your input to your classifier. And then this would serve as a sort of data pre-processing task before we train on a classifier. So that's one reason why it's useful. Another reason why it's useful is in many situations, we want to do things called feature learning, which means, yeah, for one reason or another, there's many situations in which it's useful to just extract high level information from data, right? We want to identify what is important about this data. What are the principal, maybe you've heard of something called principal component analysis, where we're trying to kind of extract like what are the most important kind of aspects of some sort of data. So this can be used, this is sort of like the machine learning way of kind of extracting just high level information from data. And there's many situations in which that's useful. And we're going to look at a modification to the basic autoencoder, which Justin's going to go over in a few minutes, called a variational autoencoder. And this is actually a lot more useful because it can do something called generative modeling. And basically, very good variational autoencoders can produce like fake images. So I'm sure you guys have seen in the news like, oh, like this machine learning model produced like all these pictures of people or all these pictures of like cats, but none of these are actually real pictures. They were just made by machines. So VAEs, variational autoencoders, can actually do this, and they're one of the most popular ways of doing this. And we'll discuss how it can do this later. But I'm gonna go back to where we were. So we talked about sparse autoencoders, and yeah, we're actually right here now at variational autoencoders. So just to wrap up my half of the discussion before I hand it over to Justin. So basically, so far what we've talked about is a model that's kind of capable of just extracting high-level features from the data. And now Justin's going to talk about an extension on top of this, which is going to allow you to do what I just said, to kind of do generative modeling to kind of make like a very common application of it is like making fake pictures. So yeah, I'm going to stop sharing my screen now and hand it off to Justin.
Awesome. Thanks, Paymon. Okay, are you guys able to see the? Oh, I'm seeing this much right now. But... Are you guys able to see the slide?
It's frozen for me. I mean, are you on slide 3 right now?
Sorry, let me get to. Awesome. So,
Wait,
like Paymon mentioned,
Justin is frozen for me.
it's still frozen.
Yeah. Maybe I can share and then you can just tell me when. Oh, it's good now.
Awesome. Sorry, I think it.
Yeah, you're
Okay,
good.
still good.
Yeah.
Awesome. Okay. So, like Paymon mentioned, this is just a variant of an autoencoder. So, whereas we had just regular autoencoders, we're going to be moving on to variational autoencoders. So, from a very high level, the only difference between the two is in the way in which these autoencoders are encoding their information. So, specifically with variational autoencoders or VAEs, they're going to be encoding the information that it gets from an input image or whatever source as a probability distribution. So the way we actually do that is we're going to put a constraint on the encoding portion of the network that forces the representation space to actually be vectors that represent a normal distribution or a unit Gaussian distribution. So what this looks like is, again, like Paymon mentioned, it's going to be some sort of regularization term or other forcing terms that kind of bound our output from the encoding side into this probability distribution. And then the idea is that this distribution will be representative of the entire space of possible, let's use, for example, images. So the possible input images that we can push into our model. So from this distribution, we are going to sample a particular latent vector from this representation space, pass that into the decoder portion of our network, in which we will use this sampled point to recreate the original image. So the main idea is that if we give the decoder a sample vector from this probability distribution, it can effectively produce a realistic representation of whatever input we passed in originally. Okay.
Yeah, and I'll just add, so the reason why this doesn't work with like a normal autoencoder, so if in a normal autoencoder, because you're not representing the latent space as a probability distribution, what happens is if you just randomly sample a point in your latent space, it's very likely not going to like represent anything meaningful, because in your normal autoencoder, you're just discretely like trying to encode information. There's no sense of a continuous distribution. So for example, in your latent space, there's going to be certain points that if you sample those points, you're going to get a good reconstruction, because maybe like when you trained the model, like it saw this specific image of a cat, and then it's saying, okay, this specific, like if I go towards this specific like point in my latent space, then I feed that to my decoder, then it will like perfectly reconstruct this image of the cat I've seen before. But if you move to some other random point in the latent space and you sample it, because you weren't modeling the space as a probability distribution, that point likely isn't going to actually represent anything. And then when you try to decode it, you're just going to get a bunch of nonsense. So that's why it's the whole like use of the VAE is it allows you to do this because you're modeling it as a probability distribution.
Definitely. Yeah, great. Thanks for that clarification, Paymon. So if there are no other questions, we're going to move on to sort of a example of the architecture. So the structure itself will be similar in concept to regular autoencoders, but it's going to differ within its implementation. So again, as our input, we will have an image, let's say, of this cat, and then we're going to pass it into our encoder network. And from this, we're going to be trying to extract information about the representation space in the form of parameters for a probability distribution. So again, if we're trying to model a Gaussian distribution, that entails a mean and a standard deviation. So assuming that we have a multi-dimensional representation space where these are going to be encoded, or these are going to be represented as vectors, because we have many dimensions for our representation vector and our latent space to live in. So that's why it's a vector, multi-dimensional. Okay, so from these parameters, we're going to sample a particular latent vector from this latent space. And then using the sample, we're going to pass it through our decoder network and hopefully reconstruct our image that we originally passed into our encoder. So at a high level, it's very similar to the regular autoencoder. It's just within this kind of like under the hood part, we're changing how we are representing our image. So are there any questions about this in particular?
I don't really understand what's the difference between like the normal autoencoder and variational autoencoder. Like, is it like one type, or it's like the same thing but like just more detail?
Yeah, so you can think of like you said, a regular autoencoder is just kind of your basic autoencoder. So that one, you're going to be, again, pushing in this input image into your encoder network. And then from that, you're going to be getting a vector that represents that image. And then we pass this vector back into our decoder, and then we hope to get that original image out. The variational autoencoder is just a different type of autoencoder in which instead of having a representation vector, we're going to be having representation probability distribution. And then from there, let's say we have a normal distribution, we're going to pick a point, and then from using this point, we're going to pass it into our decoder, and then hopefully get a reconstructed image that is similar to the original image.
Yeah, so basically, like, yeah, you're right to say, like, the variational autoencoder is like a more specific like autoencoder. Like it's essentially an autoencoder that has additional restrictions placed on it, and additional restrictions placed upon it, such that it can perform some more optimal tasks for us. So kind of what I was saying earlier, like a big difference in the way that they work is in the like when you look at the latent space, and so when you look at this sort of green vector that's on the screen right now, like in the normal autoencoder, like any particular, like if you look at the space and then you just randomly sample any like random vector from that space, what you'll notice is that like 99.999% of the time, like that point is not going to actually like represent like a compression of any given specific image, or it's not even going to be remotely related to any like specific image, because what happens in the normal autoencoder is that it's just like going to learn, like it's going to kind of assign a very specific point in your latent space to like represent the higher level features of some input image that you give it. The only difference in the variational autoencoder is instead of that being assigned to a specific point in the space, it's assigned over a probability distribution on that space. So basically, like you'd imagine that like the mean of that distribution would be exactly like where the point would normally be optimally in a normal autoencoder, and then the standard deviation would mean that in this sort of like local space around this point, these spaces are also going to be related to the compressed version of a specific image. So then optimally, if you sample any given point around some like specific point that represents the compression for a specific object, then you're going to get an output that's like hopefully, like Justin said, still pretty similar to that object. If you sample more closely to the center of the distribution, chances are you're going to get a better output. But it's not like you're just going to get a completely nonsense output if you're a little bit off, because it's modeled as a distribution.
Yeah. So we'll kind of go over this difference within the middle a little bit more with some more examples. So if we can hold on until then, but thank you, Paymon, for that clarification. So we're going to move on now. So the intuition for VAEs, we're going to express it in this example of having to sort a box of crayons by their color. So a regular autoencoder would simply sort the crayons into discrete piles. So like red crayons, pink crayons here, more cool tone, bluish, purplish, greenish crayons in this side of the whatever we're sorting it into, like on the floor. And the key takeaway from this is a regular autoencoder is going to sort these into discrete piles where there's not really a relation between these different piles of crayons. Whereas a variational autoencoder is we're restricting by regularization techniques and other similarity constraints to make these piles kind of close together in order for there to be a sort of interpretation of what this intermediate space between the piles represents and what that looks like if we were to reconstruct like a crayon from this. So again, to put it more abstractly, we're going to look at this sort of more general example. So like Paymon alluded to, there are different criteria that make a latent space beneficial for us. So specifically and more formally, what makes a regular latent space are two criteria. The first is continuity, and the second is completeness. So first, continuity is the concept that two latent vectors, when like picked close to each other, they should exhibit some sort of continuity, meaning that they should be kind of similar to each other. So if they're close to each other in a geometric sense of this latent representation space, they should have some sort of relationship to each other. They should be similar in some way, meaning that if we had a cat image get pushed into this particular point in space, we'd expect for a point that is like a little bit away from it to also be a cat image when it's reconstructed. So that's continuity. The next one is completeness. So completeness represents that within our latent space, we can pick any such point within this latent space to sample, and that should be able to be reconstructed into a meaningful image. So again, if we look at this left side, this is an example of irregular latent space. I don't know if you guys can see my pointer, but this purple dot, we can think of this as not really being a real encoding of, like, let's say a cat or a dog or a horse image into this particular point. But let's say we were curious and we just picked this point and passed it to our decoder for it to be reconstructed. Once reconstructed, we see that it's a nonsensical shape. So this doesn't satisfy the completeness condition for a regular latent space. Whereas in this side, if we were to pick any sort of point within this region, within this latent space, this would be a meaningful shape. So that's the difference in distinguishing conditions for a regular latent space. Once again, continuity and completeness.
Yeah, and you can
go
ahead.
ahead. So that's something that we're going to be looking for when we construct these variational autoencoders and their latent space probability distribution.
Yeah, and just going over this, kind of looking deeper into this example, so we can kind of understand like why certain points, maybe like given the surround on. So I'm looking at the right side, by the way. So the regular latent space, we can sort of see why certain points, given the points surrounding them, are going to represent reconstruction of the object that they do, right? So the pink, the orange circle or the orange point, like if you sample that point and then you run it through your decoder, it's gonna like make a picture of a triangle, right? And then we can see like if you sample a point close to it, that's like between the triangle and like the circle, you're gonna get sort of like a triangle with rounded edges, right? And that makes sense because like the circle is something that has very round, like is just completely round, right? The triangle is like has 3 sides and they're all very sharp. So if I go between sort of my triangle and my circle in my space, then I'm going to get something that's sort of between a triangle and a circle, right? But if you were to do that same thing on the left side, because you're not modeling the space as a probability distribution, you're just modeling them as discrete points, then every single point just represents a specific object, and there's no sense of like all the things Justin was saying, continuity or completeness, because now if I sample like some like that purple point that's on the screen, we would expect to maybe get something that's like similar, like the rounded triangle again, right? Because it's sort of between the circle and the triangle, but then we just get some nonsense object because the space isn't modeling a probability distribution, it's just modeling very specific points. So there's no relationship between like the different points in space.
Awesome. So that's kind of like the high level overview. So we're going to move back to our crayon example. So again, if we have a jumbled mess of different assorted crayons, our regular autoencoder, we would expect to kind of sort these into discretized piles. So we see we have like blue crayons here, some brown crayons, white crayons, all in discrete piles. Whereas with the variational autoencoder, we expect to have this sort of continuous and complete probability distribution and therefore latent space for potentially sampling crayons. So we can see that these kind of act as a sort of gradient in which we can understand relationships between colors and similarity between them. So this lends itself useful when we're going to be sampling these from these probability distributions for reconstruction. Okay, so what does a loss function look like for autoencoders? So for regular autoencoders, it'll just be the reconstruction loss. So the loss between the original data representation. In our case, we've been using examples of images. So the loss between our original images and our reconstructed images. And this can be actually quite variable depending on how you're using them. So one example is like a pixel by pixel difference. So we can look at just like the residual between different pixel activation or values. Another could be like structural similarity. So between two images, there's this sort of concept of similarity, and we can measure that loss, as well as if we use something more formalized, like let's say like MNIST dataset, where there's a clear objective of classifying images correctly, we can run, or we can even look at and see, oh, we identified this image as a 2, our original image. When we reconstruct, can we identify this image as a 2? So we can actually incorporate some ideas of like cross entropy loss for our regular autoencoders. So moving on to our sparse autoencoders. So again, it's going to be that same reconstruction loss as we see with regular autoencoders, but we're going to add in this constraint of L1 regularization so that we force our model to be more sparse and our representation to be sparse. So again, L1 regularization is just we're pushing the absolute value of our weights towards 0 for our minimum objective. And then finally, variational autoencoders, we're going to, again, have that reconstruction loss that's kind of common with all the autoencoders. Something called the KL divergence. So this is a measure that serves as a distance measurement between different probability distributions. So again, our goal, our desiderato was for a normal unit distribution a Gaussian distribution. So we're going to compare and see the distribution we come up with and our desired normal Gaussian distribution and see how similar they are in order to push our model toward to have a unit normal Gaussian distribution. So yeah, it'll measure the difference between two probability distributions. Sorry, I'll wait for this. So in this case, the output latent distribution and prior would usually be a Gaussian distribution. So we want them to kind of be similar. Okay, and then we kind of went over this, but just with this new information in mind, we use autoencoders so that so it helps downstream tasks for other machine learning sort of objectives, right? So we can think of dimensionality reduction, in which we have a large input space. So we want to reduce this down toward more meaningful features. And then it can also act as a form of data denoising. This can be very effective in feature learning. So if we don't know which features are particularly relevant for our image, we can, or whatever input data type you have, you can use autoencoders to find out which portions of your data are really important and really substantive toward your input data. Pre-training, so using this trained encoder side, we can actually, if we think about like what it's really doing, we're learning a rich representation of our features at that particular point within our latent space. So if we think like, oh, the machine has a good understanding of our data at this particular point, we can use these weights as an initial starting point for other types of tasks. So we can just port these weights and then push it into a new architecture. And then if we want to add in like a fully connected layer at the end for some other task, it might work relatively well. And then we went over these sparse encoders to learn sparse feature representations, and then variational autoencoders, since they learn a probability distribution, they lend themselves especially useful toward generative modeling. So like Paymon kind of mentioned, if you're interested in creating deep fakes, like that goes like hand in hand with these variational autoencoders. Great. So now we're going to move into the coding section. So just a couple of demos. Let me know if you can still see everything. Can you see the notebook?
You're good.
Great. So this is kind of some materials that we have drafted up for you guys. If one of you can drop the link to the
Yeah, I got it.
Notebook, that would be great for everyone to follow along. So we're not going to actually like run through this cell by cell, but I've already ran through everything. So it should work on your guys' end. Let us know if there's any issues with actually running the notebook. But essentially what we're doing is we're setting up this encoder decoder structure, specifically in the special case of an autoencoder. And we're training this, and we're trying to apply this toward our MNIST data set. So MNIST, once again, is the canonical example of a classification task for computer vision and machine learning, in which we have these handwritten digits and we want to classify them into 10 different digit classes. So first, we have our initial input images here. And then after, without training our model, we have these decoded images, which definitely need some work to resemble our original images. So we'll try and do that through training. So just initially, we're plotting out our encoding. So this is actually the latent space that we had kind of referenced within our presentation. So as we see here, not really meaningful to us, especially since there hasn't been any training done. So we're going to be adding some more layers and then more effectively training these things. So again, this is kind of the same plots that we saw above. And then this is one where we have constraints of L1 regularization, so that we make these representations, this latent space, a little more sparse. So you guys can play around with and try and improve this accuracy. And then finally, we have our variational autoencoder. So this is going to be learning our probability distribution instead of an actual discretized representation space. So we see here, this is kind of a plotting of our data distribution. And I believe this is our latent space actually. And then I'm assuming that when we sample across this sort of probability distribution, we can see different types of classes even. Like at this top right corner, we see like zeros. The top left, we see like more like 9-ish looking things. And then down here, we see 2s and maybe 3s around here. So we can see like there's a gradient and some sort of essence of like intermediate values in which they're like similar or connected. So that's kind of the generative power of VAEs.
Yeah. Now.
So another.
Or,
go ahead.
Okay. I was gonna say, does someone want to like try to like say how this kind of image that we're looking at right now would be different if we were using like a normal autoencoder as opposed to a VAE? Like what could we kind of expect to see if we kind of looked at the same exact output?
Will the picture be more like discrete but not continuous? Like the color?
Yeah, so yeah, that's correct. And like what that would mean is that like we might have like somewhere like if we sample like in some specific location, like we might get like in the top left right now, like it looks like we're getting a 9 at the top left. So like in our autoencoder, we might like in our normal autoencoder, we still might get like a 9 in the top left. But then if we move like a little bit like down and towards the middle, like we can see we're still like kind of getting 9s on our autoencoder because our variational autoencoder because it's modeled as a probability distribution. But if we just ran it for our normal autoencoder, we would probably have like some completely nonsense looking value if we went a little bit down and towards the middle. Because like we said, like we've been saying, the points in the space are modeled discretely, not as distributions. So only like specific points are actually representing like certain compressions or certain like higher level features of our input.
Great. Okay. So I also enjoy these like VAE simulations. So we tried to find another one for everyone to kind of play around with. So let me drop this in the chat. So this is another resource that we found. This one is actually in the scope of using another topic reinforcement learning to get an agent to be able to play a video game, but it employs a VAE in a portion of it. So if we look here, these are original frames from the video game Doom, if you guys are familiar. So we're going to take this as our input image, pass this through our encoder, get a sort of latent space representation that we denote as Z. And then from this, if we were to sample it and run this through our decoder, we should be able to get a frame that is generally similar to our original. And we see that this is relatively similar. So yeah, so there's actually a cool widget that allows you to kind of play around with these different vectors within this latent space. So we can see that these are kind of similar, but if we tweak, like let's say this one, you can see like this vector specifically, maybe this one is representing like a fireball coming toward you, or I don't know, like a bullet. I also have not played Doom, so maybe fireball. So we can see like this, if you toggle this, like it changes our reconstructed image. So if we think about what this is representing, it's saying like within our probability distribution, if you were to choose like different values within this direction or this dimension, this will correspond to like this fireball either being there or not being there. And this is the same as like other ones. So this is a little more subtle. If you guys can look like toward the right-ish, you can see like that sort of changing. So different features represent different things and they might have different effects, but there's like this sort of constant concept. So changes within this latent space will represent changes within your reconstructed image. And you can also like randomize like this screenshot and change it up, like maybe see other things and like randomize the toggles too. So really cool. There's also like one more example, and feel free to look through this sort of repo as well for other like inspiration or just like background on this stuff. But this is another application toward like a racing game. So you can see like this feature specifically will change like this curvature at the top end of the track. And we can like load in a random one. And this will like also like very, very subtle changes here. Like maybe, and this one you can't even see all that much, at least to us, right? Yeah, so feel free to play around with this. I thought it was really cool when I stumbled on it. Hopefully you guys also think so. But let's get back to that presentation, and Paymon, you can go ahead with whatever.
Yeah, I mean, I was just gonna say, can you go back to the example actually that you were
Sure, yeah. Sorry about that.
No, I was just gonna say, like, you can imagine, right, how this can be used to generate like fake images or like not real images, right? Because any if we have these conditions that we talked about of a good latent space, I think it was continuity and completeness, right? If we have these things, we can sample like any point in our latent space and we'll get something that like actually like probably makes like looks like something real in to the human eye, right? Like we can clearly identify like the changes that are happening as we like sample different points in this latent space, even in this car example, right? Like Justin was just saying, like if you move a little bit along this dimension in the feature space, like you'll see like, yeah, this one just like changed how the like where the road is, right? Like now the road is in a different position. And this is something that clearly to the human eye, we can see exactly how these things are changing. And I think that's very amazing, right? And you can imagine like in more complex examples than just like a car on like a track in a game, like if you're doing this with like dogs and cats, like maybe if you sample a point that's like in between like dogs and cats in the latent space, the representation for dogs and cats in the latent space, and you sample and then you just decide to sample a point that's between them and then run it through the decoder, then maybe you'll get an image of something that looks like something between like a hybrid of a dog and a cat. It's like they might have like cat ears, but then it might like have a dog's nose, something like that. And then you can and that's not like that's like a fake image, right? It's not like an image that we actually took in real life. It's something that the model generatively created. So I think that's really cool.
Awesome. So I'm going to try and get back to the presentation. So that's kind of the wrap up of it. We just wanted to show you guys like a demo. But apart from that, we really appreciate if you were able to fill out our feedback form. Again, this is our last workshop for the quarter. We really appreciate you guys coming out, especially those like returning attendees. We really appreciate your support. And we want to make these things better for future iterations, future quarters. So your input is really appreciated. And obviously, if you have any questions on the content, feel free to stick around. We will be. So ask away if you do have any questions. Otherwise, thank you so much for your support throughout the quarter, and good luck with the rest of the quarter exams and everything.
Yeah, I also just want to thank everyone for coming out, of course. Everyone who's been here for all the Advanced++ workshops. It was really fun. This was, I think, all three of our first time teaching Advanced++, and it was really fun. So thanks for everyone who's here and supporting. And with that, Varun, I guess if you have anything to say, if not, you can just end the recording.
Yeah, I guess that's about it. Thanks everyone for coming out, and see you next time.